So let's start by looking at this video. This looks like some kind of microorganism, maybe a bacterium, which is swimming at small scale, and it's small enough that it's affected by thermo-Brownian fluctuation. In fact, what it is a small piece of plastic, micron-sized piece of polystyrene, which has been turned into an active colloid. So this is the topic of what I want to study. As you can see, it doesn't superficially look much different from a bacterium. But generally speaking, it's obvious to us that nature has inspired development of science and technology, and now that we're going basically down in scale, everything we're making is becoming more and more sort of fine structured, as it were, at small scales. It's about time to look into nature at small scales and basically try to find good examples of things that we can do later on in the future, but from a synthetic or an artificial point of view. So basically, I'd like to start by this cartoon schematic of a living cell, just highlighting a few things. I don't have any names up there, so if you are scared by these big names in biological literature, as I am, this one should not be a problem. So here is the nucleus of the cell, and what we have stored in it is basically some kind of code. It's written on DNA, at least we know that. And the way the schematic suggests is that, in fact, the piece of DNA which is folded inside the nucleus of the cell is more or less densely packed. And yet it is a storage device, which means that every single bit of it, so imagine this is a micron long sphere, the cell itself is typically 10 microns. Every bit of it, to the accuracy of a few nanometers, has some kind of code, binary, or maybe using a few more letters, code written on it. And when something is needed in the cell, that information needs to be accessed at that particular location, copied, and then passed over to some kind of factory which uses that information to synthesize functional agents. So that factory is, roughly speaking, this sort of labyrinth structure over here, basically that takes these little pieces of the code and uses raw material which is available to synthesize larger functional agents, and the material basically needs to be taken from outside, so that's the exterior of the cell. You need to have some kind of transport mechanism to actively bring things from outside to the center, to this area, which is basically the main factory, and then there will be a lot of waste materials, so you need to get rid of those, and the same transport mechanism, so imagine something like a available network, will take them out and dispose of them. So, as you can see, cell is not basically a parcel of some chemicals which is randomly mixed, living on diffusion. It is structured, and basically everything in there, if you want to wait for diffusion to take things from the cell to this factory here and then get rid of the waste material, it will never happen, it will never work. So you have to have some kind of directed active mechanism for motility, and basically couple that to the right chemical reaction and so on, so that you can generate the right functional agents that will do their work. You have other things, for example, these things are energy factories. As it happens, living cells use currencies of energy. So basically, McDonald's has a headquarters in there. It generates these, burger sandwiches, and everyone eats them. Right? They don't ask questions. They don't want variety. It's the same for everyone. The advantage is, they just sit somewhere at a corner. They make these sandwiches and fill the entire space with them. They're called ATP molecules, but we don't really need names. And then some guy here who will need a bit of energy will have that available. And basically will consume that, the product of that, so that energetic molecule will be burned into other products that will need to be basically put together back into the same currency. And that will happen here in this factory by consuming energy which is taken from outside. So we eat sugar and so on, and then they are converted in this factory. So, okay, and then one more thing I forgot to mention is some kind of dynamical scaffolding structure. So the cell itself needs to have a shape, needs to maintain its shape in a dynamic way. So sometimes it needs to be a sphere, sometimes it needs to elongate for reasons. And all of that can happen in a dynamic way using these active scaffolds. And similar type of scaffolds will also basically connect the center of the cell, which is the center of all these activities, to the membrane, to the interface with the outside world, for the purpose of the basically transport of materials and so on that I mentioned. So imagine that's every single living cell. We have many of those in our bodies, and then there are organisms that are just single cells. So if you can have a unit like that, say 10 microns long, it's always more or less the same size, and it more or less has these sort of elements, maybe in slightly different ways, but these elements in them. If we can engineer things like that, then we can make devices at that scale that would behave like living things. And that should be that will be the sort of main direction that technology will go in the future, and maybe your generation will be the one that will actually achieve that. Okay, so now we want to do something. It's a very ambitious thing. As it happens, humanity has been in this kind of position in the past, and I have here a little lesson from the history of flying, which I think it sums up what I would like to say at this point. So people have seen birds for a long time and wanted to make something that would do exactly that, so fly, and people tried different things. There's this particular example that I could find this is an English translation from a very old book of some person who wrote the account of the experiment done by Ibn Firnas in the 9th century in Andalusia, and wrote about it. So what he did a few other things, but he basically attached a couple of wings to his body, went up on the tower, basically jumped, and then according to the testimony of trustworthy people, he flew a considerable distance as if he had been a bird. So far so good. There's the but. He forgot to place feathers at his back, so basically some kind of mechanism to help him land. And because he ignored that, so that small oversight meant that when he landed, he basically crashed and he broke many ribs and he nearly died. So it was an oversight because he looked at the bird and then he said, okay, let's identify the main ingredients that I need to do this. Let's make something that looks like that, and then put them together and operate the machine. Ultimately, we built flying machines. The Wright brothers did it right. And if you notice the date, it happened after the full development of fluid mechanics. So Newton, Bernoulli, Navier, Stokes, etc. These people formulated fluid dynamics. They wrote down the main equations. You could solve them. You could find the right geometry, the right design, the right shape that would do exactly that. And what's more interesting, I think, is that what they ended up making doesn't actually look like a bird, right? It doesn't flap wings. It doesn't have all those elaborate structures. A lot of the details that are there actually were not needed for this particular purpose. They could make a very small, simple design that would have the key features being identified from the science, right? And then they achieved exactly that, and they could optimize it for their purposes. So the planes that we make these days, are much better at serving humans than any bird is, because they are optimized for other purposes, right? So this is more or less what I have in mind when I say we should look into living cells and try to learn from them and make things that will basically mimic them. So I don't mean literally going out there and following exactly every single detail. I mean trying to basically pick up the important ingredients from the science and then build from scratch what would be the best components, functional agents, the smart materials that I had in my title from the bottom. Okay, now this idea of looking into biological systems from the point of view of the physics and chemistry, in fact, was first highlighted by an unlikely person, Erwin Schrödinger, when he wrote this book, What is Life? He was giving these lectures in Dublin. So in fact, what got his attention was that we have these incredibly complicated systems, living creatures, and yet we know the fundamental equations. We know Schrödinger's equations for quantum mechanics, and then at the classical level, other things. So in principle, we should be able to use our knowledge of physics and chemistry to explain everything that is going on in living cells. Of course, if you read the book, you don't find the answers to all of these questions, but it was more important to ask the question and address it at that time like this. And that book in 1944 inspired a whole generation of biologists and biological physicists, including the people who, Watson and Crick, who discovered the double helical structure and explained the double helical structure of DNA here at the Cavendish lab. Okay, so after the introduction, basically this is what I would like to do. I would like to take the particular example of molecular motors. These are the motors that I explained that living cell are responsible for the transport. They convert chemical energy into mechanical work, directed mechanical work, so the work that could be prescribed. They do that at, say, a few nanometer length scale, which means at a scale in which thermal fluctuations are very strong, and they typically would overwhelm everything. So it's very surprising that they could do something which is not overwhelmed by it. It's as if you're basically trying to generate a signal with a noise level which is, say, 100 times more than the signal itself. You have to do it in a very careful way. So basically, we would like to ask the question, can we design from scratch something like that, something that can convert a locally available source of energy, let's say chemical energy or maybe light, or other sources of energy, into mechanical work and deliver mechanical work. And basically, this class of problems that I call active colloids, I would like to introduce. It's one example. There are other ways to do that, and if you want, we can discuss them after my talk. So I will only focus on active colloids for the rest of the talk. So basically, I would like to see if we take a colloid, a polystyrene bead, let's say micron size, something we can even find in our McDonald's, actually. So, you know, how can we make it active? And by that I mean something like that. So make it swim in a directed way, or tumble around a circular trajectory, or spin around itself. Right? These are all active colloids that are made in the lab by Steve Evans. How can we basically, once we make them active, how can we get active behaviors out of them? Or in other words, if we compare their behavior with just normal Brownian particles that are also very mobile, say at small scales because of the thermal fluctuations, what would be the difference between the behavior of those, and how can we differentiate between those two? And what kind of parameters do we have to play with the difference? So let's say the activity that we explained can be tuned with something. And then if we understand one of these active agents, when we put them together, what happens, how do they interact with each other, and if we learn enough about these interactions, how can we engineer behavior out of them? So in other words, design them such that when they see each other, they would form some kind of aggregate of a certain shape, and then do something which we have anticipated. So ask them to do. So emergent collective behavior out of this. Okay. When we take a random, when we take a a colloidal particle and make it active, we need to drive it away from equilibrium. And for that we need to choose a mechanism. And I'd like to use the generic transport mechanisms that are, basically they come under the names of Phoretic transport we are familiar with. So first one, electrophoresis. You have a colloidal particle which has charges on it, so it's say negatively charged. You put it under an externally applied electric field, it moves. The motion, if you think about it, is slightly different from, say, motion of a charged dust particle in vacuum under externally applied electric field, because we need to worry about the fluid dynamics which is involved. But in principle, it's the motion of a charged particle in an external gradient of a potential. And now you can do other types of Phoretic transport mechanism. If you change the potential that you are applying, all you need to do is basically generate some kind of generalized thermodynamic potential gradient which will generate, basically within the context of linear response theory, will generate net motion. So thermophoresis is motion under external temperature gradient, and this has been in fact studied since the 19th century already. Osmophoresis is motion of semi-permeable, say, vesicles. So this is a sac of some maybe chemicals or not, but it has these holes, and they don't allow the molecules to go in or out, and that means osmotically interior and exterior are separated. Water, on the other hand, could pass through, so that generates osmosis. We know about osmosis when we have a single semi-permeable membrane. If you turn it, fold it into a spherical capsule like this, then you can get it to move if you apply a gradient of the concentration of that solute molecule. You can have motion in gradient of concentration even if you don't have a semi-permeable membrane. That effect is called diffusiophoresis and was studied by Deryagin first, and that basically comes because the solute molecules interact with the boundary, which is here. It's basically zoomed in, so this is the surface of that colloidal particle, and we are looking very close to the surface. As you can see, if there is a gradient in the concentration, so if there are more particles, let's say on this side, on the right compared to the left, there will be a fluid flow towards the concentration if that interaction is predominantly repulsive, to somehow lower that interaction, that build-up of repulsive interaction between the solid molecules and the surface. Now, this is a very hand-waving argument. I will clarify it a bit more on the next slide, but before doing that, I'd like to emphasize that all of these Phoretic transport mechanisms are force-free. And that means, that means different things for the different mechanisms, but it means that they can be used to make something which is self-propelled, because when we build something which is, say, swimming on its own, we don't want it to be dragged by some external force. We want to have an internal mechanism generating stresses and so on, multiples of stresses, so it's a pattern of stresses, maybe time dependent and so on, but nothing external, because if you're dragging a particle, a colloid, through the solvent, that's not swimming, it's basically forced motion, and you need to have this giant always doing the mechanical work for you. It's not an autonomous form of transport. Okay, so let's have a look at the equations. Now, if you have survived liquid crystal hydrodynamic equations, I think you can survive these. These are much simpler. Basically, what we have is a combination of Stokes' equation for the fluid, which describes the motion of a viscous fluid. So I'm ignoring inertia here, starting from Navier-Stokes equation. That's this one. Eta is the viscosity of the solvent. V is the velocity, P is the pressure, and force, F here is the body force which is acting on the fluid. I need to describe basically the continuity equation, if you want, for the solid molecule. So I have the concentration C, and I have the flux J. Flux J has a part which is basically the diffusive flux, so that's diffusion coefficient is mobility times kBt. Gradient of concentration, so that's just Fourier's law. And then I have this contribution from the body force. So if I have a solid molecule, at that point, that solid molecule will experience a force which is basically the gradient of the potential it experiences when it interacts with the wall. So capital F, which is force on a single solute, if I multiply it by C, I will get the volume density of the force acting in the fluid. And then I multiply that by the mobility, I get the second contribution to my flux, and then there could be an advection term, although you could ignore that if that makes things complicated. So I have the continuity, which is d by dt of C plus divergence of J is 0. And in stationary state, I can just use the divergence of J equals 0 part. I also have the incompressibility for the fluid, so that's divergence of V equals 0, which I can apply here and get an equation between the Laplacian of pressure and the divergence of the body force density. Divergence of J equals 0 gives me a similar equation that has Laplacian of concentration, divergence of the body force, and then this advection term, which we can ignore. For the moment, if you combine these two equations and eliminate the body force acting on the solute and on the fluid as well, basically what you get is the Laplacian of this combination, P minus kBTC, is 0. Let's say we are ignoring the advection term. And that means this combination should be a smooth function because it has to satisfy Laplace's equation. So at least it should be continuous, for example. Now, why is that helpful? Because when you approach the boundary here, when you get close to the wall, you have this very strong interaction between the solid molecules and the wall. So let's say Leonard-Jones interaction, which has a very strong power law, or the exclude volume interaction, which excludes the presence of the solid molecules exactly above this line. So that's a very singular interaction. What that does is that basically they changes the components P and C in this combination, but because of this equation, the combination P minus kBTC should remain smooth. And that's what I need to take to my next slide. So imagine I have this boundary layer, as I call it, and this combination is constant roughly near the boundary itself. Out here where the interaction is not active, so W is typically something, as I said, like a Leonard-Jones interaction, so it has a very short range, a few angstroms, and then it dies. Out here I have a gradient in the concentration and no gradient on the hydrostatic pressure. So basically I'm not pushing the fluid, but I'm maintaining this concentration gradient for the solid molecule. When I get close to the boundary layer is modified by the interaction potential, and for example, exactly on the boundary, because of depletion that I mentioned, solute concentration should be exactly 0. So that's a very, very abrupt change compared to the condition I had before. And if you want to still maintain the condition that this combination is constant or smooth, going from here to here means that now you have to have a gradient in the hydrostatic pressure such that P minus kBTC will remain the quantity that it was before. And that means the fluid within this very thin layer, so imagine a few angstroms, which is the range of the interaction of your Leonard-Jones potential, experiences a gradient in the hydrostatic pressure, which means experiences a flow in that. So you will have a very thin layer in which the fluid flows, and then that would set a boundary condition, if you want, for the fluid flow outside of that thin layer, which is going to satisfy normal Stokes equation. So just with the boundary condition, which you can get from this, from resolving this very short-range interaction, you will get basically the full equations to solve for the system. Now, by way of a brief comment about the nature of this mechanism, so it's very tempting, in fact, to describe the motion diffusiophoresis as if we have a cloud of these solute molecules asymmetrically, basically exerting some kind of osmotic pressure on the colloid, you know, as if you have a gas and then basically you have these elastic scattering you can use kinetic theory, and basically you would expect that after the interaction of this gas with the colloid will move to the left, but that will mean that the gas itself will move to the right, so that overall momentum will be balanced and conserved. And then you can say that, okay, I will use this force and balance it against the Stokes friction and get the swimming velocity. It turns out if you do that, first of all, you get the wrong answer in terms of, so if you put in numbers, the numbers will turn out way too large, and the scaling with the size and other effects will come out wrong. And also the velocity for the solid molecules will be against the direction of the colloid itself. So you will not have a stationary system of the colloid and the solid molecules that will move together. But if you do it right, and that means solving all those equations that I explained, what you will get is a stationary solution in which the solid molecules and the colloid will move together to the left, despite the fact that they are having these dipolar forces between themselves. So the total system, which is the combination of these, will move to the left, and that's because it's doing it in the solvent, and the solvent is taking care of momentum conservation. Okay, so let's move on. What we wanted to do with this Phoretic mechanism was basically use it to make something self-propelled. So basically you want to do self-diffuse geophoresis, and to do that you can take a colloidal particle and half-coat it with, say, a catalyst, and then you put it in a solution with uniform concentration of a molecule that the catalyst breaks down. When the catalyst does its work, it will generate a concentration gradient, so you will have more molecules on the right compared to the left, and that generates propulsion. It will be to the left if the interaction between these solid molecules is predominantly repulsive. It will be to the right if it's predominantly attractive. And what's interesting is that wherever this goes, as long as it finds the fuel molecules, it will break them and generate the asymmetry it needs for propulsion. So this is basically the catalyst acts as the engine of this motor, and these molecules will act as the fuel of the motor. You don't need to have the molecules maintained in an external gradient. You can just have them with uniform concentration. The motor itself will basically through the catalysis, will generate the gradient that is needed for the propulsion. So this is one example of such a motor. And you can make it as small as you want, so even 10 nanometers will do, and it will swim in a directed way, but there are buts and problems and so on, which I will talk about next. Right, so just the final word on the analysis. Solving that Stokes equation that I mentioned, you need to put in this slip velocity, so-called slip velocity, which is basically proportional to the lateral gradient of the concentration. And there's a parameter here which I call mobility, and that is basically controlled by the range of the interaction, as you can see through this equation. This relates slip velocity to the concentration gradient. If I solve for the concentration gradient in the bulk, by solving reaction diffusion equation with the boundary condition that on the surface this catalysis is going on, so alpha here that I call activity will be the rate of introducing these additional molecules in the solution on that particular point, on that hemisphere, and then it will be released in the solution, and then through reaction diffusion it will generate a fuzzy asymmetric concentration gradient. So basically what we have here is a system in which two parameters, the mobility mu and the activity alpha, will determine the non-equilibrium behavior that I'm describing. And you can note that both of these parameters could be both positive and negative. Alpha could be positive, which means you're releasing particles. It could be negative, meaning the catalysis is basically working as if that point is a sink for the particles. So if you remove one particle, alpha for that will be negative. Maybe you can turn it into other things, and then alpha for those will be positive. Mobility could be negative as well if the interaction potential is predominantly attractive. So you can see all you need is to make this exponential bigger than 1. And then you would get something negative for this squared length, which is bad notation from my side. Okay. with the analysis, you can play with the different things. For example, you can probe what kind of symmetry breaking you need, what will be the effect of geometry, what's the relative importance of activity and mobility, and also you can do this kind of calculation for other types of phoretic motion, including self-thermophoresis, which is, I hope I will have time to get to that, because that's the only bit that will have photonics in it, and I hope to make some connection to what you guys are interested in. Okay, so let me maybe skip that in the interest of time. If you put in, so the part that I skipped basically was telling us that these motors don't go on straight line. After a while they get, through rotational diffusion, they lose their orientational memory, and that time scale goes like the cubic power of psi. So if you choose a bigger sphere, it will maintain its course for longer. Now, you probably have noticed that concentration decays like 1 over r, and that's very similar to electrostatic potential or gravitational potential. And I have this alpha parameter, the activity, which is basically telling me how the field around one colloid, which is generated by this alpha, decays with distance and basically is seen by other particles. What other particles do with this field in this non-equilibrium problem will be different from, say, normal electrostatics or gravitation, because they have this other parameter mu to determine what kind of response they will have. So we can have a situation, despite the fact that this is very similar to electrostatics or gravity, you can have a situation in which the velocity that is felt by particle number 1 is not the exact opposite of the particle that is felt by particle number 2, because this one is controlled by the product alpha 2 mu 1, and that one is controlled by the product alpha 1 mu 2. So if you want, you have two types of charges, and each particle will have, number 1 will have mu 1 and alpha 1, and number 2 will have mu 2 and alpha 2. So that's how it generates the field and how it responds to other people's field. And these should not, well, need not be the same, and it could generate a situation in which action and reaction are not the same. For example, this guy is attracted to that guy, but that guy is repelled by this guy, right? This is a complicated situation. And that's because it's a non-equilibrium system. So you can study this kind of problem and, say, study how it leads to self-assembly. Let me just show you a movie. So these are A and B particles that start from a random distribution in the dilute limit with these tendencies. So alpha has a +3 charge and B has a -1 charge. So they find each other, they make partnerships, and then they take off. And then they form different types of molecules, so AB, AB2, AB3. In this particular case, the positive valence of A is 3 and the negative valence of B is -1, which means that you would expect from equilibrium for them to make AB3 as the stable molecule. Turns out AB2 is the more stable molecule, and it's a molecule that can exist in two different types of isomers. So it could exist in a linear form and also in a form which is planar with this angle. This one is self-propelled and this one is inert, so you can make these gains with designing these colloidal molecules with different functionalities. You can tabulate them, you can get ones that have spontaneous spin, like these ones, and so on. You can get macromolecules, etc. Right, so this is also some complicated stuff about collective behavior. I think I won't have time to cover those. As I showed you initially, these have been made in the lab, and you can characterize them. You can study the swing velocity as a function of the fuel concentration. Characteristically, mean square displacement, when you have the propulsion, will have a parabolic shape, so that's because you have a net propulsion velocity on top of the diffusive behavior. This is a behavior you see in catalytic reactions, say enzymes. If you're familiar with this, is similar to Michaelis-Menten behavior. An initial linear increase in the velocity as a function of the concentration, and then an eventual saturation. And that's because of the catalytic activity of the colloid. So let me skip a few things to get to the photonic part of my talk. So, as I said, you can use the same type of design. So take Janus particles with metallic coating. I forgot to mention the previous one had platinum. This one is done with gold, and then if you shine, if you irradiate them with a very sort of with defocused laser beam like that, you can get absorption on this end, and that generates heat locally, and that leads to a temperature gradient across the body of the colloid, which will self-propel it or make it self-propel via this other phoretic transfer mechanism. So it's thermophoresis, which is, so basically if you think about this, these particles, each of them is a source of heat, like a point source of heat, and it's also moving around with a velocity arrow. So it's a self-propelled particle which is generating heat, and the heat that is generating the temperature, because of that heat, will decay like 1 over r and will be felt by other people through a drift velocity which is proportional to the gradient of the local value of temperature. And that coefficient here, dt, which is called thermodiffusion, or when you divide it by d, is called the Soré coefficient. That can have both positive and negative signs. So you can have a situation in which these colloids repel each other, or a situation in which everyone attracts everyone else. So let me skip that, just show you a few numerical solutions. So in the case of repulsive interaction, if you make this geometry, so you confine them in a weak potential, and then you irradiate them to make them active, what you have is a buildup of temperature in the center and a depletion of the colloids from the center because of this effective repulsive effect. So they will basically accumulate near the boundary, giving you a very, very hot core in the center. If you go to the attractive case, it's similar to gravitational systems. It generates a buildup of temperature in the center, and also they form a sort of gas with a characteristic size, and that almost looks like a star if you're interested to push this gravitational analogy farther away in line with the previous talk that we had. If you increase the coupling constant, you can make things that look like structure formation. So initially you make smaller things that later on at a slower stage feed into each other to form a larger structure. Eventually you get a single one. Yeah. You can have instabilities. This is a 2D simulation. That's a finite time instability. So you start building things up, and then at some point something happens. What happens is in fact formally equivalent to thermal explosion, because the equation that you have is Laplacian of T, heat conduction equals a source which is exponentially, so it has exponential feedback on the temperature itself. And that's the exact same equation that was first written. So this, if you go to the right page, Nando Lifshitz will give you that reference, 1939, explaining basically combustion. In this case, if you do the experiment, don't worry, that's going to be almost a fizz in your solution, but you know it's safe to wear goggles if you want to do the experiment. I suspect you will just have jets of these basically vaporizing locally the water, but nothing too drastic. And you can call this a supernova if you want, because this is basically a situation in which accretion material is bringing in more heat or act as an exponential source for heat, and is feeding back to the rate of the heat generation. And at some point there's a finite time singularity that generates this colloidal explosion. Okay, we did another simulation taking into account the fact that they cast shadow on each other finite size of the colloid. So now it's a bit more delicate because the particles that are not only action and reaction are not the same, but say this one who is completely in the shadow will not see any activity because it doesn't receive any light. This one does receive light and generates, so this one is self-propelled and is generating a velocity which is pushing or pulling along this guy in the shadow. This one is somehow at the interface receiving a little bit of light and also acting a little bit as a source. So if you make a study of particles taking into account this effect, what you get is a swarm. So the red here shows the particles that receive light. Light is coming from the top, and you are moving with the swarm, so you're in the co-moving frame. This is the top view. These blue guys are in the shadow and they don't receive light. And it's a self-organized structure which is moving like this, but leaking very, very slightly, so it will die eventually after some long time.
What are the green dots?
Are there any green dots?
No.
For that I need to have to go back to Jack and ask him, but I thought this was only coded for 2 types. In fact, there are 4 populations in these swarms. The ones at the core here, the ones exactly in the shadow, the 3 ones outside, and the ones that are left behind. So we later on do this, but I thought this movie was coded with 2 colors. So I'm colorblind anyway, so I won't be able to tell you. We see interesting things in these swarms. We see streaming inside, so circulation, which is almost similar to similar to inertial systems, but this is a completely viscous system. We see fission, so little swarms will be ejected if you crank up things a little bit. So in this movie, if you watch out in the top view, at some point something will be thrown at your face. Okay. There one. There'll be another one. Anyway, this is a slightly larger coupling constant, so the intensity of light is larger on this one, and it's a bit elongated, more elongated compared to the previous one. It's wiggly, more dynamic, and also it undergoes this kind of fission. I mentioned waves already, so I think with that I can conclude, and maybe if there are questions I can go back to the stuff that I skipped. But what I want you to take away from this talk, I was telling Ivan this morning that I realized my talk is more like an appetizer than a main course for this particular school, because you're interested in other things, but you can take rough ideas from this and apply them to your system, because you can always do very interesting things with liquid crystal systems, and if you know how to manipulate them with light. If you drive them away from equilibrium, these are the kind of things that you could use and engineer very sophisticated systems. So with that, I'll stop and thank you, and ready for questions.
Do you have actual means now to make kind of asymmetric particles?
Sorry, say it again.
Do you have some way to make such kind of asymmetric particles?
So the movies that I showed you, the ones that were, they look like real movies, they are real movies. They're made in the lab, and so the smallest we made is about, actually you could make as small as possible, you cannot see them. So with light microscopy you could push it to a couple of hundreds of nanometers, and with those the swimming velocity achieved has been 37 microns per second. So something like 50 times or 20 times its size per second. This is based on the chemistry of hydrogen peroxide and platinum. And there are other people who use other chemistries.
You gave lots of examples with this phoretic transport. What's the actual technical definition of phoretic?
So non-equilibrium transport of colloidal particles under gradients of any type of potential. So temperature, as a potential thermodynamic, basically, potential. So electrostatic potential will give you electrophoresis. There's even dielectrophoresis. I gave examples for the concentration, magnetophoresis, and so on. So anything that will move because of basically a gradient that you're applying, and it's not basically it has to be a force-free motion. So it has to come from the thermodynamics and take the whole system uniformly as a net collective.
So gravitational gradient doesn't count?
So gravitational gradient, that's an interesting question. I think in a fluid, it might count. So if you have sedimentation, that doesn't count because that's just pulling something with an external force.
Yeah.
If you achieve basically buoyancy and then apply some gradient on top of it, so you expect it not to move, but because of the gradient in higher moments, and you're in the fluid, so it's using the same structure. I would call it, but I'm not. This is, you have to ask the 19th century guys.
Do you have control over the direction of motion?
That's a very good question. That's an excellent question. So one of the slides that I skipped, let me actually go back to that, because at least I can introduce. So there are 3 timescales in this simple Phoretic transport motion. If you make it more complicated, there will be other ones. This one is the rotational diffusion time. Basically, if you have a colloid which is undergoing Brownian motion, its center of mass displaces because of the kicks that it's receiving from the fluid. Now those kicks, if you regard them as really tiny forces, they could also generate rotational Brownian motion, rotational fluctuation. And the timescale for that is comparable to the timescale of a colloid moving its own size, basically. So that's why the rotational diffusion coefficient looks like, or the inverse of it, which is the time, looks like the normal equation for the diffusion with an extra 2 factors of basically R. So that goes like R cubed, which means that if you put in numbers, there are some numbers here. For a micron size bead, the time scale is a few seconds. That means if you make something which is a micron, it will go in a straight line for a few seconds and then lose its orientational memory, right? If you make it a nanometer long, so that's 10 to the minus 3 here, to the 3rd power, that's 10 to the minus 9. So a nanometer long colloidal Phoretic swimmer will swim actually as fast as this one, because I skipped that as well, and there's no size dependence in the Phoretic velocity. But it will only go in a straight line for 10 to the minus 9 seconds, which is very short. Now, there's another time scale, that's the characteristic time for the cloud around the colloid to build its asymmetry, or if there are changes to adjust to it. That's R squared divided by D, and that's in the millisecond range for a micron-sized object. So there is a separation of time scale here. And then this other one is the crossover from inertial hydrodynamics to viscous hydrodynamics. That's in the microsecond range. So there's a natural separation of time scale here, which means we have 4 different regimes in between them behaving differently. If you are at the longest time scale up here, these mechanisms cannot give you a directed motion. You have to do something else. Something else so far has been to put a little magnet in it and steer it externally with a magnetic field. That is done already, and it's not very easy to do. But I think it should be possible to do something cleverer than that. And that's a very interesting thing to think about. We know that molecular motors are basically guided by, I mean, this is a fundamental limitation. It's not a shortcoming of this mechanism. So bacteria do that and so on. You need some kind of guidance, external rail or something which is helping the orientation, otherwise it will be lost. So what E. coli does is it has these flagella, and usually in the tumble phase they are distributed around it, and then in the run phase they are all bundled at the back, and hydrodynamics is such that rotational diffusion time, this equation here, picks up the longest length scale in the system. So if you have these little spikes that you will align and add the body length to it, for E. coli it makes something like 30, 35 microns altogether. And that gives a rotational time scale, put 35 here, you'll get something which is in the many, many minutes. So you can swim on a straight line in the minutes. When it's like an electrocuted cat, when the flagella are all spiking out, it's much shorter. So that's why it can tumble, right? It's exploiting hydrodynamics to the best.
Okay, one more quick question.
Very interesting. Just a curious question. Are you aware of anyone using surface tension gradients to drive?
Absolutely. Many people do other mechanisms. I skipped a few experimental slides that were from other groups, and also I didn't have any on surface tension, but there is the well-known Marangoni effect, which is basically using a chemical potential gradient.
Right.
But that uses surfactants on the surface, and count for both and so on.
Right.
In fact, last week we had talks on that.
You're not aware of anyone putting camphor on particles, are you?
So people do make smaller versions. So there are many groups. The one that I can remember now is there's a Japanese group that does that in Kyoto. Kenichi Yoshikawa started that a few years ago, and now his colleagues are continuing it, and there are other people as well.
Thanks. I think we should move on. Thank you very much.